Grade 12 is all about light waves and quantum mechanics. Grade 11 is understanding sound and sound waves. So if we make compressions in the air, these are sound waves. So as these compressions hit your eardrum, they get registered as sound. Okay, so this is a rarefaction right here. So you can see the depiction of the air particles. There's fewer of them. It's less dense. Then we got an area of greater density. Less density, greater density, less density. If we put the density of those air particles over air pressure, we get a sine sort of graph. So what we're doing is we're taking the depiction of the air particles and we're turning it into a sine graph. Most waves are studied through sine. Now, if we take a look at the velocity of sound in air, sound travels faster in a solid than it does in a liquid, than it does in air. In air, sound travels with a velocity of 332 meters per second. Now, you might think that's really fast, but if you're at a baseball game and somebody's at home plate and you're in the outfield and they hit that ball, you see that ball go up in the air and then you hear it. Okay, light travels much, much, much faster than sound does. Light travels around the earth several times in 1 second, where sound is traveling 332 meters a second. Now, when you're doing calculations with the speed of sound, for every degree in Celsius, temperature in Celsius, we go up. We've got to multiply that by 0.6 and add it to the speed of sound. So if the temperature was 10 degrees Celsius, 10 times 0.6 is 6. 332 plus 6 is 338 meters a second. So what you will find is you'll find that sound travels faster when it's hotter out. Now, if you've ever heard of Mach 1 before, Mach 1, what's happening here is we're talking about the speed of an object relative to the speed of sound. If an airplane reaches Mach 1, what's happened is its velocity is same as the velocity of sound. So it has to be going at least 332 meters per second. If we doubled the velocity of the object, if it was going at 664 meters per second, you divide that by 2, or by 332, you get an answer of 2. So we are at Mach 2 there. So just a couple of sound relationships that you should be aware of as you move forward. Now, frequency. What frequencies can we hear? We can hear anywhere from 20 hertz to 20,000 hertz. So if we were to diagram 20 hertz, it might be like this. If we were to diagram that 20,000, it would be like this. This would be the frequency. So frequency is the number one of these cycles that pass a point every second. Okay, so 20,000 hertz means 20,000 cycles per second. Anything lower than 20 hertz is infrasonic, and we can't hear that. Anything higher than 20,000 hertz is ultrasonic, and we can't hear that. When you're talking about frequency, you're not talking about energy, you're talking about pitch or tone. So if you've heard the terms pitch or tone, if you're into music, you will know what I'm talking about in here. If not, you might have to look up what pitch and tone are and maybe a quick video on this. I know there's a couple of simulations that help you to take a look at this. I suggest that you do that. Once again, if there are any videos embedded into the content and it is just a URL, make sure you copy that URL and paste it. The last thing that they go over in U4A2 is the whole idea of the Doppler effect. If you have a car and it's standing still and it lays on the horn, the sound waves go out like this, and that's a horrible drawing. These are supposed to be in uniform fashion all around it. When you're driving, what happens if you're moving forward and you hit the horn or you have a siren, all of the sound waves at the front of the car are compressed together. All the sounds at the back of the car are spread out. Okay, so we've got higher frequency at the front of the car and lower frequency at the end. I highly suggest you look at videos of Doppler effect because I butchered this drawing so badly. These lines are supposed to be the same distance apart in the front and the back before it's moving, but if a car is moving faster, the faster it moves, the more that we put these sound bars together, they get compressed all together, and we get what's called the Doppler effect. So it will start with a high pitch, so that's what you'll hear as a car comes towards you, and it will go to a low pitch as it goes away from you. So the Doppler effect is the effect of sound when a car is either approaching you or going past you. Go outside, go near a freeway especially, you can hear this Doppler effect. Now, one thing you're going to have to do is you're going to have to look up uses of sound in technology. So I would take a look at echolation and what it is. I would look at one medical application and one application found in nature. Like dolphins use echolation to find things. So just check your understanding of what echolation is. In assignment 2 for unit 4, you should understand that even though these are longitudinal waves, if we put the depiction of these or the density over air pressure, we can form a sine graph of them to study them. We should know that the speed of sound is 332 meters per second plus or minus or plus 0.6 times the temperature in Celsius. If you've ever heard of Mach for airplane travel, you can take a look at the velocity of the object divided by the velocity of sound to see what your Mach number is. You should understand frequency in sound, hertz to hertz. You should understand the Doppler effect. And one thing I forgot that I'm glad that I forgot to mention was decibels. And this is the intensity or the energy level, where this is pitch or tone. Decibels are the energy level or the intensity of the sound. Study decibels. It's definitely going to be on your unit test. I'm sorry I skipped that over, but what I'm trying to do in these videos is trying to direct you to what's important. Make sure you know what decibels are.